chemistry change what is a metalloid versus a metal versus, well, usually metal and metalloid. Okay? Everybody's usually pretty clear on what's not non-metals because shiny. Shiny, basically. Does it lose electrons to most of the non-metals, and is it shiny? So those are pretty good definitions usually. But the metals versus metalloids is where things get pretty contentious pretty quickly. Okay, and you can see that. I mean, look at this right here, right there, right? The normal definition for a metalloid is it has two sides touching this line, right? Except not. Except there's almost as many exceptions. What the heck, right? So, yeah. And in fact, just 2 years ago, somebody came up with a new test that they're going to use, and apparently it's actually a pretty conclusive one. So hopefully that will become less of an issue, but that's not going to be reflected in any textbooks probably for the next 10 years. Unless it's a very, very new, very upper course one. Like if he republished this one in a year or two, it probably would. Okay, because this is a pretty good author. All right, so this right here is your electron affinities for, again, some selected elements, not all of them. You will notice that this chapter actually has the calculations that you would do to figure all of these values out and the math that are behind them. I do not expect you to really go through and understand the calculus ones where you're like, I don't care if you can derive that calculation. That's just beyond the scope of this course, okay? But I do expect you to be able to do those ones that have examples and problems I'm assigning, right? Okay. And it's I pretty much hit most of the non-calculus where they've derived something that's algebraic, right? Okay. Okay, if ever I do a calculus one, please do actually let me know, because I don't know if you guys know, but I have 6 different courses that I have to prep in every week. And so my number of preps is very large, and then I don't have any materials I can just deploy, right? So I have to remake all the assignments and everything. So, and all my classes are on Monday and Tuesday. So, every Sunday I'm like, oh shit. Okay, so right here, this is actually the definition of BDE. Does anybody know BDE? Oh, you 1, 2, 3, 4 are killing me here. I am so disappointed. Bond dissociation energy. You have an excuse. You didn't have me for the organic one. Okay, it's okay. But, naughty. So, bond dissociation energy. What would a bond dissociation be? A breaking. And notice that neither of these are different or have different charges, right? And so that would homolytically breaking, right? Where it just dissociates from each other. Each of them get one of the electrons that was in the bond. Okay? And so this is essentially the symmetric breaking of a bond. It's the best measurement and definition that we've come up with so far of how much energy it takes to break a bond, which is how strong a bond would be, right? Okay. And yeah, it's starting to come back, isn't it? Yeah. So it's a beginning of organic chemistry is where we really went into these things. You actually did a little bit of these as well when you were doing Hess's Law back in Gen Chem. But you didn't really know what the hell you were talking about or why. They just started to dump the calculation on you guys, and they're like, do this. And it's always funny because you got a lot of material to cover in Gen Chem, right? In all chemistries. There's just a lot of chemistry. Okay. So this right here is a metal, and it's taking on an electron, right? And what are we seeing this? We have this material taking an electron. It gets a negative charge. What would that be? Okay, so this would be an ionization energy, but would not be the normal ionization energy you guys have probably used in Gen Chem and all that, okay? Which was losing the first ion, okay? This is the energy that you would have from gaining an electron, okay? Now, so like, for example, fluorine would give you energy out for doing this, right? That's why fluorine is so good at gaining electrons, okay? And so reactive and keeps its electrons all the time, okay? And this is just a measure of that energy. Typically, you could do it experimentally. It's specifically called an electron affinity, and these are the electron affinities.
So sorry, that saying is to take in energy in order to take in another electron?
Yes. Yeah. Normally, most elements, you would have to put energy in for them to take electrons. Okay? The fluorine, for example, gives you a lot of energy for doing it. Okay? So, for example, you can gain energy from a hydrogen gaining electron in some cases, if it's just by itself. And this is why hydrogen, for example, is a diatomic. Why it always self-assembles, right? You never see hydrogen by itself. Okay? Helium, on the other hand, you always see by itself, never gaining any electrons because it takes energy to do it. Yeah. And can you put electrons on these things? Anybody ever seen a neon sign? That's what you're doing. The old style neon signs. You're literally putting a bunch of electricity into neon originally. They weren't neon all the time, but and you're putting electrons on them, and they come off, and they give light. Okay? Yeah. And that's why they give very high-frequency lights. Yeah. And so, yeah, that's what that's showing. Is that making sense?
Yeah.
Okay. Okay. Yeah, and these are why the electron affinities here being positive numbers is why most of these things do reactions. Now, notice that it's not 0 that you really need to compare things to. 0 is somewhat of a meaningless number for this, because what you really need to compare things to for electron affinities is electron ionization, electron affinity. The average of those is how well it's actually going to hold on to the electrons. Okay? Because you can also get energy from stripping electrons, right? The other thing you got to consider is relative electron affinities. Things don't exist in a vacuum. Very rarely would you just have hydrogen, pure fluorine, pure anything, right? Most of the chemistry situations, we're going to have a combination of these things. And so, for example, which one is going to hold on to electrons better, boron or hydrogen? Which one would take electrons energetically favorably?
Hydrogen.
Yeah, hydrogen, right? And anybody remember boranes? All my Organic 1 people just did boranes. And boranes are BH3. Yeah. And so they're one of the ways you can generate essentially like a hydride. Okay, a negatively charged hydrogen. Mm-hmm.
I'm looking at like the diatomic elements. How come nitrogen? That's a diatomic, right? I'm not.
It is. Yeah.
Why is that one so low? Like compared to
The double and triple bonds.
Okay.
Yeah. Yeah. That's what's making it more energetically favorable.
Okay.
Yeah.
So if it's negative, that means it's more favorable.
It's less.
Oh, less. Okay.
Yeah. Because it's a negative EA equals the delta H.
Okay.
Yeah. And we want a negative delta H, right?
Right.
Yeah. Yeah. In the case of nitrogen, the triple bond nitrogen is very, very stable and will get stuck. But if you get it high temperatures, so you can actually break up those nitrogens, you can actually start forming nitrogen oxides, NO, NO2. And that's actually what happens in an engine. And that's actually what smog is, photochemical smog. Yeah. Now, if you have a catalytic converter, it helps convert that back to the N triple bond into form. Okay, now, Okay, we had always sort of talked and we had mentioned, and you've heard some things about atomic radius, probably, right? Especially in like Gen Chem. Atomic radii is actually a more complex topic than you'd ever dived into before, okay? And that's because atomic radii heavily change depending on the substance you have it in, okay? So for example, if you have a metallic radius, because they're suspended nuclei and a sea of electrons, okay? And that's a very good model for how they operate. The electrons don't really have very specific positions. Where exactly do you cut off that orbital ending? That 90% probability of finding electrons? I don't know. So you end up doing a radius that is essentially, you take these two, you look at them point by point, metal center, and then you take half of the distance between them. Atomic radii. Okay? Makes sense, right? That is a totally different number than if it was in a covalent bond. Or if it was a van der Waals radius. Okay? And that's because in a covalent bond, by definition, the two orbitals have to have merged a bit, overlapped. And they have to be pulling on the same electrons, right? And so suddenly, those have to have been overlapped, don't they? Okay? And so you end up with slightly different numbers. It also has an effect on the orbital from the fact that you're sharing those electrons, right? The van der Waals radius right here is the van der Waals forces causing these to stick together, and you can measure the distance between them. But again, that's going to change that radius. Okay? And again, you have here the ionic radius. This would be the radius of the ions, and these would be stuck together due to their charges, right? But the very fact that it's an ion is going to give you a different radius, right? Because if you're a positive ion, you have an extra positive charge, and that's going to pull those electrons in, isn't it? If you're negative, you have less positive to hold on to them, and so they're going to push each other out, aren't they? Okay? It's going to swell it. Is that making sense so far? Anybody get lost in that? Okay. Uh-huh.
The covalent would just be the distance between the nuclei, or?
Yes, that center point. So distance divided by 2.
Oh, so it would be the same as metallic, just a little bit.
It's the same way of finding them for all these.
Okay.
Distance between the nuclei divided by 2. But they're different numbers for all of them.
Okay.
Yeah. So if you were to take the same substance in all these, say iron, okay? You can form covalent bonds with irons, you could do a van der Waals, you could do all these, okay? You would get a different number for every single one of these. Okay? It would not be consistent in any way whatsoever.
Okay.
Yeah. And these are why it's not consistent. Is because for like a covalent bond, you have overlap. That has to happen by definition. Because you're actually mixing those orbitals for the complete substance, right? Yeah. And again, these ones right here also are banding those orbitals. Or another way of saying that's the electron C model, right? And then these ones, you're just changing the whole charge. So your effective nuclear charge changes, right? And everything about it changes a little bit. Okay. Okay. These ones even complicate even more, by the way, because there's actually several ways of calculating the distance in molecules. And that's because molecules actually vibrate. These atoms don't actually stay still in space. Yeah. So, and so they'll change from energetic conditions and temperature and everything else. Yeah. So it's a whole thing. I actually have a chapter in molecular studies that details these different R values and why you get which one and under which circumstances you could use those and how to get those. Yeah. They're it's a whole thing. Enough that you'd have to write a whole book on it. Okay. All right. So Rmax is going to be reported in atomic units, and this is actually the formula for the Rmax. And you can see here we have the effective nuclear number. Remember, as we go down the periodic table, that number actually sticks to about 4, right? And actually stops growing much after 4. This right here then is Z. That's the effective nuclear charge. Okay? And so what Rmax would be is it would be Rmax divided by N divided by N star, which is the effective one. Okay? And then this would be divided by the Z max, the Z star, which is the effective nuclear charge on it. Let's go ahead and try that out real quick. This is Slater rule, by the way. It's a theoretical radius for that atom. It is not going to give you perfect numbers. These actual experimental values will be a little different, but it's a pretty decent prediction for a nice linear calculation that's algebraic. Okay?
So I'm sorry, Z is effective nuclear charge, N is just the nuclear charge?
So N right here is essentially the periods. Okay? And then N star is the effective period, essentially. Okay? Let's go ahead and try it out. We'll do a problem. Okay, so when we look at the theoretical radius for a nitrogen atom, for example, so we have the nitrogen atom up there. It also has a table in the book that, no, I did not. Yes, I did, right here. So this right here is that effective quantum number. That's that quantum number that corresponds to the period, or the energy level, or the shell. Okay? All right.
Oh, no, sorry.
Okay. So we'll need that number in just a bit for N. Notice that for the lower periods, it actually just directly corresponds. Okay? When we get to higher periods, that's when it stops growing as much, because we get more and more packing that prevents that. More and more shielding. Okay, and so we go Rmax, we put the N over, so multiply this N over, and we get N times N star over Z star. Okay, so for nitrogen, what period are we on? Not group, period.
Oh,
2? And so N is 2. That's the principal quantum number, the period. Okay? The principal quantum number is what makes the periods, right? And so whatever period number it is, it's the principal quantum number. Okay. We go down to 2 here, and the N star, the effective one from the nuclear from the shielding due to those electrons building up in the orbitals, is still 2. There's not a lot of effect yet, because we don't have that many layers of shielding. Okay? If we were on 4, it'd be 3.7, right? Okay. And so we go ahead and plug 2 times 2, and that is 4. The next thing we're going to do is we need to get Z. So the effective nuclear charge for nitrogen in the previous problem was actually calculated as being 3.9. And so you would put that in as 3.9 right there. We go ahead and do that math. 4 over 3.9, we get 1.03. Now note that that's going to be atomic units. So we need to actually deal with angstroms here. Okay? So in terms of angstroms, those atomic units, A0, is going to be 0.529 angstroms. And so we're going to be 1.03 times that number. Okay? Okay. Now, if you have any difficulties calculating this, let me know, okay?
Can you just review that real quick?
I don't think I have the problem up here. No, I don't. Or at least I have a slightly different one. We can do this one if you want, which is a slightly different problem. So calculate the... No, this is the first ionization energy. Shit. No, I don't have that up here. Let's do this. Try out the example 3.5, okay? And email me if you guys have issues. And what I'll do is I'll make a video. And then I'll put that up, okay? Okay. Yeah. I don't have all the tables and the problem from my in here. This is actually right here, the theoretical values predicted. And then these would actually be the covalent ones. And that they have selected to compare these with. Okay? And you can see that they're in the ballpark. Sometimes they're not great. Sometimes they're better. Sometimes they're worse. Okay? But in general, they're within the ballpark. They give you fairly decent predictions. Okay? There's a lot more factors that go in for actually determining a covalent bond distance or radius. Okay? All right, so these right here are actually the trend as it goes. And what we can see is this is the atomic number right here. This is your theoretical radius. And do you notice a trend here? What does that trend correspond to? Lithium, sodium, potassium, rubidium, CS. Yeah. Yeah, you're looking at the periodic trend, aren't you? See that? Because remember, Z is just the atomic number, right? And so we're literally the periodic trend. And what we see here is the theoretical radius actually peaks at the beginning of the periodic table. And then we go down as we go along the periodic table, right? Okay. Okay, now there is a bit of a divergence that happens at 80 where mercury ends up being your big one. Okay? All right. And that's, again, just that effective nuclear charge trend that we've been seeing this entire time, right? So as you go along the periodic table, you have less shielding that's building up, but you have more protons building up, right? Okay. And so we're actually just seeing the exact same trend. I'm going to actually just sort of skip this. It's an interesting side note in depth in your book. If you get a chance, read it. It's actually kind of interesting, okay? But I couldn't figure out a way of including it that didn't take up so much time that was worth it. So the next thing we have to talk about is polarizability. Does anybody remember polarizability from organic chemistry or maybe Gen Chem? No? Okay. So this is the definition here. Specifically, polarizability, if you're going to use the exact terminology, is actually static electric dipole polarizability. Okay? And chemists get a little lazy, and we don't want to say that many words all in one, and they're kind of, unpleasant to say altogether. And so we just call that polarizability, and that's typically abbreviated as alpha, which is kind of a terrible choice of a symbol because there's already a bunch of alphas, right? But whatever. It's the tendency of electron cloud in an atom to have its charge displaced as a result of an applied external electric field. If you're doing experimental, this could be things like a parallel plate capacitor. So you put them in between two electromagnetic plates and you apply current and you end up deforming the field. Okay? But it also could be things like in organic chemistry, we just talked about in organic chemistry, a reaction where we have Br2, it comes near a pi bond, that has a magnetic field. Okay, pi bonds have magnetic fields because they're negatively charged, right? And so that actually causes the bromine's electrons to deform and move away from the pi bond, which makes the bromine a little bit positive. You all probably know this better from dispersion forces. Do you guys remember London dispersion forces? Okay, This is the same effect. The more polarizable things are, the more you're going to experience London dispersion forces. And this is why when you go down the periodic table, you have two effects happening. You have increasing polarizability. You also have more electrons. The more electrons have more states they could be in, where you have a slight positive charge on one side and a slight negative charge on the other. And so probabilistically, you get more chance of that happening. Okay? Okay, and so what we're seeing here is an example where we're taking a positively charged magnetic plate, we're putting it near an atom or a molecule, and what we're seeing is we're inducing a negative charge near the plate, because those are attracted to it, and we're inducing a positive charge here. How easily that happens is its polarizability. Okay? Okay. So if it's highly polarizable, you can easily put poles on it, right? This happens a lot with just molecules in general. Like, this happens on its own. You don't actually have to apply magnetic fields externally. You can just get a very extreme response that you can cause and, be expecting if you do magnetic fields. So this right here, the SI unit, is actually F over M, or this group of terms right here, which is basically charge density. Okay. Typically, this is actually reported in volume units, like angstroms to the third per atom. Okay. And what we're doing is we're reporting it in volume units because usually we're talking about magnetic fields around atoms, right? And so all we're really concerned is where the electrons take up. Okay. This is actually the equation right here. And so you can see that right there is the term for it. So A over V, alpha V, is the volume of the polarizability. This term right here, which is 4 pi E0, that's the permittivity of this free space, how easily those electrons can move around. Okay? And then it's 10 to the 30 on the top. And then alpha here, which is actually the static electric dipole polarizability value. You typically only report it in the volume, though. Mm-hmm.
So is that just like a number, or is it?
Yeah, you could experimentally determine that number.
Okay.
Typically what they do is we solve this down right here,
Mm-hmm.
so that we can have an easier equation to work with. And we would get this one right here. And this one is the volume that we were talking about, that we normally report this in volume.
Mm-hmm.
And that equals 9 over 2, which is 9 over 2. Yeah. And then it's the radius. So all you then need is just the atomic radius of it. And that's to the third power, because we're going to be doing a... Yeah.
So that alpha in the equation is, you said it's, what was it?
Yeah, it's this right here. Static electric dipole polarizability.
Okay. So
But normally we only want the volume component for it.
Okay.
Yeah. Yeah. So we're getting rid of everything but the volume component here.
Right.
You can actually see here that the permittivity of free space is that units right there. Okay. Let's try it out. It's easier just to try things out, right? Actually do them. So we're going to use the radial data from table 3.6 in your book, the equation 3.34, which I put right there. And we're going to calculate the volume polarizability of BE. We're going to use the angstroms to the third per atom. So your theoretical radius of BE from that table is 1.09 angstroms. We go ahead and plug that into our equation. So 9 over 2 times 1.09, which is that radius again, to the third power. What we're going to get here is then the alpha V, which is the volume component. And that's going to give us 5.8 angstroms to the third over atom. And this is more often than not, almost usually how you're going to end up using this, okay? Because all you really want from it is A over V, and it's fairly easy to find the radius. That's one of the easier things to measure or predict, okay? And so by far and away, this is the most common formula you would use. Now let's look at this. Okay, so this right here is some of the illustrations of a transitions going from ionic to the polar covalent. So right here we see hard ions, okay? And what that means is that these have perfect little ion shells, right? Can you see that? They're not affecting each other essentially at all, are they? Okay, so you have a positive ion, you have a negative ion, they're perfectly round, they're not deformed by the presence of the other, and they're perfect ion or hard ions, okay? They don't deform. We look over here, and this is more of a soft ion, okay? See how it's deforming due to the other charge? And so the positive is getting pulled over into the negative, right? And the negative is pulled over the negative charge over to the positive. Can you see that? Yeah. Nucleus gets pulled over next to the negative. Or another way of saying is the electric field, the electrons around that nucleus is getting shoved over the other way, right? Okay, everybody good with that so far? Okay. And then we transition over, and instead of being ions anymore, we're actually a partial positive, partial negative charge, right? And so that is a polar covalent bond now, okay? And so we've deformed these orbitals so much they have mixed together, right? And instead of just being deformed ions, now we have a polar covalent bond, okay? Is everybody okay with that spectrum? I'm just sort of slotting on a new part of the spectrum. So before we had talked about ion to covalent, right? And it had been a spectrum, but we kind of had just like a break, right? We had polar covalent, then bam, ion. And polar covalent to covalent was a spectrum still, right? Okay, but that's not really true. It doesn't just go polar covalent, bam, now we're perfect ions that don't deform at all, okay? In reality, there was always ions that were softer, and there was always ones that were harder. Ones that this shell here deformed almost none at all, okay? And ones this shell deforms quite a bit. And we had been using these principles before. So for example, chloride. Chloride has a lot of polarizability. It's going to be a soft ion. It will deform a lot. It would be this right here, okay? So you put that with a cation, and what's going to happen is it's going to deform a lot, and it's going to bond to that pretty well. Okay. Okay. And that's why there's it's very energetically favorable for it to be ionic. Okay. On the other hand, hard ions are going to have a lot of trouble binding back on. Okay. And typically, yes, you're probably already making the connection. A lot of these things were the strong acids versus the poor acids, right? The weaker acids, okay? For example, fluoride does a pretty good job of not deforming. Very low polarizability, keeps its electrons really well, and so it likes to be as F minus, right? Yeah. And so it has what's usually considered a lot of hardness, okay? It's a hard ion, is what a lot of people say. And so chloride and bromide, on the other hand, are softer. And so they're really good at being negatively charged ions because they deform a lot, right? They're very good at not having something attached to them because they can deform a lot, and the waters can help them deform, and then they can fit in with all the waters attached to them and a hydration shell, etc. Okay? Okay. And they can also make bonds easily, right? So whenever we were talking about like nucleophilic attacks at organic chemistry, right? This is that same principle. So we can deform, we can reach in. This would be like the start of making a bond. And then if you're going to actually make it, you'd slide over here, right? Okay. And so it was related. So this is actually the hardness of an atom. This has to do with, again, how tightly the nucleus attracts and holds its electrons. Hard atoms, or ions, usually is where it actually matters. Is going to have a large charge density. This would be the effective nuclear charge here, divided by R. And so those electrons are extremely tightly bound. They can't really move around a lot. Okay? It would be like a very strong magnetic field real close to it, right? If we get further away from that magnetic field, what's going to start happening to our things? Can we slide them? Yeah, we can slide them easier, right? Okay, if we get further away, we can slide it easier. If we get less effective charge on it, because we have a lot of like layers in between, we're going to be able to slide those things around easier, right? Okay, and so that nucleus is going to exert a significant influence over its electrons. Soft atoms are going to be large, polarizable. They'll have electron density that is squishy is a good word for it. It's more diffuse. It's more malleable. It's squishy. You can move it around more. Honestly, if you just think of these as like water balloons, you have the like water bed and you can barely mold that. And you have the water balloon and you can like squeeze it and move it around a lot, right? Yeah, and that'd be a pretty good analogy. And then you have like a ball that you can't move anything at all, right? Yeah, it'd be a very hard ion. And that soft ion would be like the water balloon where I can deform it easily, right? And it moves those things around, and the water would then be the electrons. Okay. Ralph Pearson developed the hard-soft acid-base theory, which is the HSAB. Was anybody taught any of this in Gen Chem? Yeah, they don't teach it a lot in Gen Chem anymore. I've noticed that the books have all moved away from it. The professors have moved away from it. We just don't do it in Gen Chem anymore. And you may sort of see some of this language that you may have heard something that sounded very similar to it when you were talking about like the strength of acids. Okay? And that's because a lot of this is the underpinnings of those. Okay? And so the chemical reactivity of your molecules can also be affected tremendously by this hardness and softness. If you remember your like nucleophiles, I was using very similar language during that, right? And I was talking a lot about polarizability. This would be a theoretical underpinning for that. Okay? Okay. So the global hardness of an atom or molecule is going to be defined as half the difference in energy between the ionization potential, the IE. Remember that ionization potential that we were talking about, how easily it loses its electrons, and the electron affinity, EA. Okay? And this is why when we got to that, I didn't want to jump all the way into this yet, but when you asked me, like, why does that make this compound, it's because you're only looking at half of the energy equation. Okay? You need both parts to really determine which is going to be more stable and if it'll easily react and make something. Okay? And both parts together get the average. This will give you that hardness factor, the global hardness. And that will give you a much better idea of the reactivity of these things. Okay? So let's go ahead and use those theoretical radii given in table 3.6 and our conversion in table 2.4. We're going to calculate some global hardness of BE in units of EV. So the theoretical radius is 1.09 from that table. If we take that value and divide this value by the Bohr radius, which is 0.529 angstroms, we're going to get an R value, capital R, of 2.05 Bohr. Okay? That is that same hydrogen radius that we had used in those previous calculations. We were talking about hydrogen back in chapter 2, right? Okay. So that's the Bohr radius. Okay. We need that because that is that capital R right here, multiples of the Bohr radius. Okay? So it's just how many multiples of the Bohr's radius are we? because this is calculated in multiples of Bohr radius. And so we're going to go ahead and substitute those in. Our E here is going to be 1. We have 2 times 2.05, which is that multiples of the Bohr radius. And that's going to give us, for our hardness value, 0.243 AU, atomic units.
So we divide the 1.09 angstroms by the 0.529 angstroms.
You got it.
I'm sorry, why do we do that?
So this equation here, right there, is going to end up being in R units. These R units are going to be in terms of Bohr radii because of the definitions of these right here. So this is actually a derived form of this.
Okay.
Yeah, that we can more easily plug numbers in and deal with. Okay, and whenever we derived this, everything, so the only Schrodinger equation we can actually solve perfectly is, well, up to like 3 or 4 years ago, was actually the hydrogen one. Everything beyond that's incredibly difficult, and you can't solve to be exact. Okay, so when you're talking about in terms of energetics and electron equations, a lot of these are actually in multiples of Bohr's radius, which is hydrogen's radius. Okay.
Is that E squared? That angstrom? Is that what they use for the example solution? 1.09 squared, or like? So what?
It's just 1.
Okay. E is just 1.
Mm-hmm.
Okay. Oh, okay. I see what they use that for. So that's for the R value.
No, R value is 2.05.
But they got that.
So
by
if we look up at,
You said they got that by dividing the 1.09 by the Bohr radius 0.529.
yes,
Okay.
Yeah.
Yeah.
that's this R value right here. Yeah. And the 2 here is just part of the equation.
Yeah.
Okay. All right. And so we do have to do an conversion of AUs to EVs. That's that same conversion factor you've probably seen a few times now. So 1 AU equals 27.2114 EV. And so we take our 0.243 number, multiply it by that, 27.2114, and that's going to give you 6.63 EV. I don't remember if I put the table up here through 9. I did not. Okay.
Is E squared always going to be 1? Or
So this has to do with actually, are we going to do anything that's not 1? Let me think. Okay.
okay.
Yeah. In fact, if you want more on this, I can send out a video. Okay. Okay. Let me actually. Would somebody be willing to send me an email? Send a video on E squared.
Yeah.
Okay. Okay. Thank you.
No.
Okay. So one of the last things we need to talk about a bit is electronegativity. So this is actually Linus Pauling, 1932, which is one of the most award-winning scientists of all time. By the way, he said you should get a kit, model kits. Have you guys got model kits? So you're laying Linus Pauling down, okay? No, he did. In one of his Nobel acceptance speeches, he attributed his success to model kits. Okay, so he defined the electronegativity as the power of an atom and a molecule to attract the shared electrons to itself. His electronegativity scale is still the one that's almost in exclusive use in every chemistry class I've ever seen. However, there are multiple scales of electronegativity, not just this one. Okay? But this is the one you would have seen in general chemistry and organic chemistry, okay? And that's the scale that goes to 4.0. This has been arbitrarily assigned, and that's for the element of fluorine. Okay? So that's that one that goes up and to the right. You get larger and larger values of electronegativity, right? When you get up into the fluorine there, that's 4.0. That's the highest one on the periodic table. Does anybody know what the values are for the noble gases? They don't have values. Yeah. So no value for the noble gases because they don't make bonds. This is how well you hold electrons in a bond, right? So fluorine's the largest one on there. Yeah. You can tell that it's a earlier attempt at it because it doesn't take into account some really weird edge cases, right? Like fluorine's the highest number. It's arbitrarily 4 for the highest number. Does anybody know where you get 4.0 as the highest number? What's your highest grade?
4.
So it's actually a pun. 4.0 is an F. Yeah. Anyways, moving on from that. So we actually have other models as well. Now, typically what you would have done, and you'd use this for, is you would take these electronegativity values that were experimentally determined, arbitrarily set as 4 being the positive, the largest, and you would have taken the difference between those, and that would tell you what sort of bond it was, right? Okay, now there are different scales that are have more situations they can be used for. Okay, so the Mulliken-Jaffe scale defines electronegativity based on atomic parameters, namely the average of the valence ionization energy and the electron affinity. You're going to notice that that is very, very similar to something we were just talking about, right? It's very similar to hardness, isn't it? Okay, and so we're actually starting to see these concepts starting to blend, right? And yes, that is largely on purpose. So hardness was also something that, for example, fluorine is a very hard ion because it has a lot of electronegativity. It can attract the electrons very tightly and hold on to them. So when it gets into a bond, it's also going to pull the electrons towards it and hold on to them really tightly, right? Okay. And so they are very related concepts. This is actually the value that they do, and it's chi is what that symbol is, that sort of cursive-looking X. And this is MJ for Mulliken-Jaffe. I don't remember. Which is usually expressed in EV, electron volts. In 1989, Lee Allen actually proposed an electronegativity scale based on entirely on spectroscopic data. So you could easily do these in spectroscopy and be able to just easily solve these without having tried to do a lot of theoretical work and having to do a bunch of different experiments that you don't have to just shine light at something. Okay. And so, more specifically, that's going to be the average valence electron energies obtained by gas phase atomic spectroscopy. Anybody ever heard of a gas phase atomic spectroscopy? No? Okay. So, gas phase atomic spectroscopy usually involves taking an open flame and then you just spray your compound in it and you look at the spectrum of light given off by burning it. Okay? It's a very quick test. And so Allen's spectroscopic electronegativity depends on the configuration energy, which is CE, or average valence electron energy of an atom. Okay. And so epsilon is this small e looking thing. Okay. Okay. So I'm just going to say EP if everybody's okay with that. Okay. In ES, just because epsilon is a lot more word. So this is the 1 electron energies of your valence p and s orbitals. They can be measured from spectroscopic data, where M and N are the numbers of p and s electrons that occupy these orbitals. More accurately speaking, the energies EP and ES are going to be calculated from the average of what would be 2L plus 1, 2S plus 1, which is the multiplets of your ground state with those of the single S and P ionization configurations. So it's a bit more complex once you start actually going into it. You can see why this is not used in general chemistry, right? Like, this isn't horrible. But this is just... do you guys know what multiplets are? Okay. Yeah. So what multiplets are is when you have an unpaired electron. Okay. When you have paired electrons, your multiplet is 0. Okay. Because what states could they possibly be in? 1, right? They can only be in one state, and so spectroscopically you get no changes. You just get one state, and so you have multiplying of it by 0. Okay? One state, nothing else. When you have unpaired electrons, you start getting different states it can be in. Okay? If you only have one orbital it can be in, then you have two states of up and down, don't you? Spin 1/2 and spin -1/2. Okay? If you have multiple orbitals, it could be in multiple different orbitals. They're all degenerate. But depending on how you boost energies and boost things up into them, you can start having different states they exist in, right? And so multiplicity is going to be the number of paired electrons multiplied by the different dimensions it could be in. And it can give you, under certain circumstances, multiple peaks of the same thing. Okay? So when you start looking at the spectra of stuff, instead of seeing one peak for a transition, for an electron boosting up into a higher energy orbital, you could see 3. And those would be the different states it could transition. Right? So you could get like up, going into the next orbital, down, going into the next orbital, up. You get down, going into the next orbital, up, going into the next orbital, down. Okay, you can get all these different energy states. Okay. And this is referred to as multiplicity. Right. Okay. And because we can have these in these different atoms, because we have different numbers of unpaired electrons, right? Like if we go across the periodic table, we get different numbers of unpaired electrons, right? We start introducing multiplicity. Okay, let's do something fairly easy, which is we're going to use our data from table 3.3. We're going to calculate that chi-spec for nitrogen. Okay? So we look at the electron configuration for nitrogen, and what we look at is the valence shell. That's all we need is the valence shell. And so what we see is that is 2s2, 2p3. Does everybody understand how to get that valence shell for nitrogen? So we go on the second period, right? We go across the second period. The S block is that first one. Everybody see that okay? Okay, fantastic. And then that's full, isn't it? So 2s2. And then we go to the next block, and that's the P block, isn't it? And so that will be 2p. And then we count along until we get that number that's in there. And so we're nitrogen, so we're 3 in, aren't we? So 2p3. Everybody okay with that? Fantastic. Okay. And so if we look on table 3.3, the energy of the 2p atomic orbital for nitrogen is 13.1 eV. If we want kilojoules per mole, that would be 1260 kilojoules per mole. We look at the 2s atomic orbital. That's 25.5 eV, 24.60 kilojoules per mole. So we can go ahead and take the formula from equation 3.46, which is this one right here. And what we can do here is we can go ahead and take these numbers that we got from our table, plug them in. And then these values right here is these M values. Now, when we look at these M values, M and N are the number of p and s electrons occupying those orbitals. So how many p and s electrons do we have in those orbitals? Yeah, 2 in the s, right, and 3 in the p. Okay. And so the EP goes with the 3 because those are for p's, right? The s's goes with the 2's because that's 2 electrons in the s orbital. That's the energy for s orbital electrons. Okay. Okay. And then we go to the bottom and we get m plus n. So again, that's just the number of electrons in each of those orbitals. By the way, you'll notice that will match up with the group number, won't it? Everybody see that okay? Because the group number on the first 3 periods is just the number of electrons in that shell, right? And all you have is the s and p orbitals, so there you go. And so we go ahead and take that over 5 once we calculate that. So 3 times the 1260, 2 times the 2460. I'm going to stop saying these things. I don't think you guys need it or care. Or, like, it's not helping, is it? Okay. Okay. So we just do the math. Can I just do that? Uh-huh.
Where does the 1.75?
Oh, down here?
Yeah.
Okay. So we got down to this number right here. Okay. And notice that this number here is going to be this next one where we're approximation. Wait a second. You know what? I forgot to write that down, and I am drawing a huge blank because I am freaking tired. All right. Wow. I am having a day, aren't I? You know what? I may have to get back to you on that because I am just drawing like this massive blank, and I am half asleep. Yeah, I normally, shit, I forgot to put that in. God, what is that? It's a conversion factor that's that approximation. It's what I normally have been referring to as this part right here. It is a approximation or a they move together in the same amount by this factor, but I'm just forgetting the name for it and drawing a blank right now, and I'm gonna have to get back to you. I'm sorry. Yeah, I am. Wow.
But so the other part of it is just trying to eliminate the units, so it's unitless.
Yeah. Yeah. So this is like a K value. It's a constant that you would use for this that goes to the chi-spec, the electronegativity here, from your CE. Okay? And it would be the same sort of thing as you would use for like a rate constants, that sort of thing, where experimentally derived value for the same deal. I just am drawing a complete blank on its name, and I didn't put the table, the information you would use to get it. So, yeah. Shit. I'm gonna move on because I'm obviously not, yeah. Can you send me a message to add that? Yeah, thank you. God. Oh, man, I need some freaking coffee. All right. Anyways, there's another 3 electronegativities that are possible variants on this. 3 other ways of calculating electronegativity. They're all different chi-spec, chi-AR, chi-alpha different ways of calculating it. Okay, they will give you slightly different numbers depending on the way, but they should be pretty consistent with each other. Okay, because they've more solidified on a more universal units that are actually used, right? Which is things like kilojoules per mole, right? Which is an energy per mole, rather than an arbitrary 4 number. Okay. So this right here is actually how they compare between them for the different atoms. Now, note that some of these can't be calculated for certain atoms because, for example, helium doesn't normally form bonds, right? And so, for example, if you use, let me see if I can get to fluorine. Right here, you can see that we have they all match to that 4 arbitrary scale, but they're calculated from actual energetic units now. Okay, and you can see that they all match up pretty well with 4, but they're slightly different because they're slightly different situations that they're derived from. For example, some of these are from bonds, right, that are formed. Some of these, however, are from, for example, burning the thing and letting its electron shoot off it, right? Okay. All right. This would be the chi alpha, by the way, formula. And you notice that uses the alpha V right here, which is that polarizability that we had talked about before, to calculate it, which is this right here. Why am I just pulling up damn blank? Okay. The last thing we have to talk about in periodicity is actually a trend that we've already talked about a little bit, and that's the metalloids, actually, are an example of this, okay? And this is diagonal trends. So you may have noticed that in this periodic table, this periodicity, we had 2 things that were moving that were changing as you go up and to the right, right? And if you have a trend that's changing in these 2 directions, right, then what's going to happen as you go along? You're going to get same ratios, aren't you, as you go diagonally. And so theoretically, you could have actually arranged the periodic table to, instead of the groups we currently have, which are based on valence shell properties and valence shell chemistry, we could have arranged it based on the effective nuclear charge to shielding ratios, right? And it would have had the diagonal ratios, which are the same. Okay? And so, for example, we have these pairs right here, lithium, magnesium, BeAl, boron, silicon, that have the same ratios for those. And so they have very similar properties in certain situations. Now, we didn't do that because, honestly, the periodic trends going down the groups are just much more dominant in almost every case, okay? And are just better predictive trends. However, there are properties that are better assigned and better predicted going diagonally. For example, your IE and EA, your electron affinity, ionization energy, those are actually both increased going up and to the right in the periodic table. And so if you were to look at these, you can actually predict them better by going diagonally than you would be able to do in a single group. And you may have noticed that if you go down the group, they change, right? Considerably. You go across the periods, they change, don't they? If you go diagonally, they actually are pretty close. Yeah. And of course, the one that you actually probably kind of already associated with this would have been the metalloids, right? The zigzag diagonal line, which is the metalloid properties. And guess what the metalloid properties are most closely associated with? The ratio of IE to EA, right? Ionization energy to electron affinity. The same sort of ratio of how well do you hold on to your electrons, how easily do you give up your electrons, right? Okay. And if we look over on the periodic table, what we see is, for example, that actually changes as you go down the period, doesn't it? So carbon, does that lose its electrons as easily as silicon or germanium? No, that's something that changes, doesn't it? And that's why things become metallic as you go down the periodic table on the same group, right? Is because that ratio is changing. Okay? So they lose electrons more likely as you go down the periodic table because your ratio changes, doesn't it? Okay, this right here is actually a really cool example of this, which is the crystal structures. So if you look at Be and Al, they actually have very, very similar crystal structures, despite the fact that you have AlCl3, 3 chlorines for every Al, versus BeCl2, which has 2 chlorines, right? But they still give you similar crystal structures. And that's a tetrahedral coordination, actually. The last thing we have to touch on, and hopefully this will end this, okay, is this is Einstein's theory of special relativity. Normally we don't see this in very small things. However, there is a certain situations where it actually pops up quite regularly, okay? And that's the fact that when you have electrons, they're very light, right? And you have a nucleus, it's very heavy, and the attractions can become extremely powerful, okay? And so what you're actually seeing is that, okay, how much special relativity do you guys know at all, if any? Nothing? Okay. Okay, so special relativity, I'm not going to give you the whole spiel because it's actually has a lot of aspects to it. But the important part we need is as you approach the speed of light, your resting mass, as you just sit there and you're nowhere near the speed of light, is a different number than if you were to be moving near the speed of light. Okay? And that's because energy is directly proportional to mass, isn't it? Okay? And so remember that E equals mc squared? It works both ways, doesn't it? Okay. That E equals mc squared was only part of an equation, though. It was E equals mc squared plus kinetic energy plus relativistic factors, which is what we're now talking about. Normally we get rid of those because we're talking about an object at rest, right? It's not moving. So there's no kinetic energy, and we don't have to worry about any of those relativistic factors because we're near the speed of light, right? No issue. Okay. In a situation where you start approaching the speed of light, your mass is going to start increasing as you approach the speed of light. This is relativistic mass. And this is actually something like why a photon actually has some sort of mass. It has zero resting mass, and it has relativistic mass. Okay? And so it only exhibits mass because it's moving at the speed of light, and it's always moving at the speed of light. Okay? And so that's, for example, why stars lens light. Did you guys know that? Okay, very massive objects, when light passes by them, are affected by gravity. And so stars will actually bend the light around them and lens it, so the objects around them are actually amplified. So that's why if you've ever seen any of the pictures looking past our sun, the objects just around it look bigger. Yeah. It's gravitic lensing. Okay? Anyways, okay. Was that enough that you got the idea that objects exhibit more mass when they're going closer to the speed of light? Okay. Okay, so now, if you have a larger mass for your element, it's going to have stronger electrostatic pull on those electrons that are near it. Okay? So far, we had been talking about the ones in valence shells, right? The ones very far from it. But the stuff really close to it's going to get pulled really, really hard, and it's going to be accelerated really, really hard. Okay? And because of that large accelerations, we can actually get up into the speeds in excess of 108 meters per second. And so we can actually start getting actual fractions of the speed of light in those like 1s orbitals next to a heavy element. Yeah. And so this causes the electrons' masses to actually increase. Okay? And so in the smaller ones, your Schrodinger non-relativistic model is fine. We don't have to worry about relativity. Nothing's getting accelerated anywhere near the speed of light. Yay. And it makes it very convenient when we're working up in the periods 1, 2, and 3, which is the vast majority of chemistry, right? No issue. Fantastic. But once we start working down in the lower periods, we actually have to start dealing with this a little bit. And so some of our predictions start veering off in that base model. And that's because those electrons are actually relativistic. They have greater mass than they normally should. Okay? Okay. And so, again, if they start traveling near the speed of light, their mass starts going up. Okay? And that's relativistic mass. Okay, this right here is actually how this is related. The MRREL is actually the relativistic mass of its electrons. M0 is that normal rest mass you usually think about. Okay? And this only happens if you start getting near the speed of light. V here starts getting into the speed of light, right? Okay. Can you actually have larger than the speed of light, by the way? No, that'd be imaginary numbers, right? Okay. Okay. And so right here, this is the R value of the accelerated electrons that have smaller average radius, because as you get heavier, they're going to go down in more, and you're actually going to start shrinking your entire radius. And so you'll have a noticeable deviation from that radius that you thought it should be. Because the electrons are accelerating more, they have more velocity, they're actually a little bit heavier. Okay? Not a huge amount, but enough to notice. Okay, I think I'm past time by a lot, right? Okay. Would you guys send me an email? I need to talk about that N value, which I'm just completely freaking blanking on, and is really bothering me now. And I need to talk about, what's the other one? E2, yes. Would you send me an email for that?
Yeah.
Okay, thank you very much. Okay. Was there any other example problems or anything you wanted me to talk about? Okay, it's probably not going to be until sometime either very late tonight or tomorrow, because I teach until 5 and yeah. And then I have to answer all the emails that I accrued throughout the day. And so I don't know if I'll get time to actually record something. But, oh my God.